Let's just wait another 30 seconds or so. There's only 9 people here at the time. Okay, good morning, everyone. Hope you had a good weekend. I sent an email out yesterday because I thought last week I had changed the due dates for a couple of things, and apparently I didn't. So the only thing that was due last night was the 4.3 quadratic functions. I said to take a look at it, see how it went. Today, I plan on covering quadratic inequalities, and then I'll get into polynomial functions. I'm going to talk about synthetic division. So let's see how today goes, and then I will adjust homework assignments based on how far we get. Any questions over the quadratic functions? Everything's okay? What we had talked about last time with quadratic functions was basically this set of steps on how to graph a quadratic. And so on your exam, which is, let's see, when's that exam coming? Not for a while, so it's after spring break. So we got quite a ways before our next exam. But on that exam, I will allow you to have a reference sheet. And on that reference sheet, you'll probably want to put these steps on how to sketch a quadratic. We're going to move on though, unless there are any questions. No one seemed to have any questions on sketching quadratics.
I have a question. How to do it backwards? Because on the homework it said it gave us the graph and then the vertex and then plus I believe it was the y-intercept.
Yeah, so that was one of the last problems, right?
Yes, sir. I just didn't know exactly how to do it backwards, so I couldn't really.
Okay, yeah, no, that was a problem that I gave that. Remember I told y'all like there's always gonna be like one homework problem that is gonna be like out there. That was the one that was out there. So I contemplated taking it off, but I left it there just to see if anyone would ask about it. So this goes back to when we were first talking about quadratic functions. I gave you this format for a quadratic, ax squared plus bx plus c. That's what we call the standard form. So when it comes to quadratics, they actually come in 2 forms. The first is standard form, which is the one I just mentioned, ax squared f of x equals ax squared plus bx plus c. And that's what I based the steps on sketching on. The other form that you can see a quadratic is called the vertex form. Okay, now this form looks like this. F of x equals a parentheses x minus h squared plus k. So that is the vertex form of quadratic function. And what you'll notice here is that the letters, you know, in the standard form, the a, the b, and the c, we use that to solve the quadratic. Well, to find the x-intercepts, if we need to use a quadratic formula, we also used it to find the vertex, right? The vertex required that we calculated h and k, and then the a told us up or down. Well, in vertex form, you still have the a. Okay, so whatever a is here, that a still dictates if it opens up or down. But the rest of the formula is different in the sense that you have h here and k in the actual formula. So I don't know if you have it in front of you, but do you know? do you remember what the vertex was that they gave you, or? No,
No, I don't remember. I think it was, I don't
I'll just make it up.
remember, honestly.
I'll just make it up.
Okay.
Let's just say we have a parabola that has a vertex over here of, let's say, -2, 3. And let's say it has a y-intercept down here of -5.
Oh,
Okay.
Professor,
Yes.
I wrote it down. I know the dots, the points that they gave us for that problem.
Uh-huh.
It was -2 and -4 for the vertex,
Okay.
and 0 and, and -8.
Okay, so -2, -4. Like that was the vertex. I'll put V here. And then the y-intercept was 0, -8.
Yes, correct.
Okay, and they wanted you to find the equation or the function,
Yes.
right? Okay, so here's the way this goes. The first thing you do is you realize that this is H and this is K, all right? Because that's what the vertex is. So you can come up to your function right now and you can just replace the H and the K with those numbers. So I'll put A, then be careful here because it's X minus, now H here for us is -2, so I put -2 there, and then squared, and then plus the K is -4. Okay, so let me clean this up. This means that the function f of x equals a, and then the minus becomes plus, so x plus 2 squared, and then I can just put -4 since I'm adding a negative number. Is that clear so far? Okay, now the only thing we don't know is what a is, right? We don't know what a is, but they tell us, they give us this other point, right? And this other point says that when we plug in for 0 for x, the output of the function should be equal to -8. So let's just take this function here and let's just say what this will be. If I plug in 0, I will get a 0 plus 2 squared minus 4, but that must be equal to -8. Does that make sense? Okay, good. Now if you look at this, we have a here. This is like an equation where we can solve for a. We can just 0 plus 2, that's 2, and then we square it. This becomes a times 4 minus 4 equals -8. That's the same as 4 times a, so 4a minus 4 equals -8. And see, I have just a little linear equation now. So I can just solve this for a. Add 4 to both sides. And we get 4a, this cancels, we get equals over here -4. And then divide both sides by 4, and we get a is -1. And now that we know what a is, we can go back up here and we can say, all right, we know the function now. The function is a, which before we didn't know what it was. Now we know it's -1. And then x plus 2 squared minus 4. That is the function. There's no way you could have done that problem without me giving you the vertex form, which I didn't have a chance to do at the end of class. So I anticipated there'd be a question, so I'm glad you asked. Let's just verify this. I'm going to show you that this actually works by going to Desmos, and I'm going to plot, first of all, the points they gave us, -2, -4. So that's that red point. That should be our vertex. Then the point 0, -8. Okay, and that's this point here. And now what I'm going to do is I'm going to type in the function we just got. So I'm going to put f of x equals -1 x plus 2 squared minus 4. And you can see there that that parabola goes through that vertex and through that point. And that is the only parabola that does that. There's a unique parabola that has this is a vertex and this is a y-intercept. Make sense? Good, good question. Anything else? I probably won't give you something like that on the test. I'll probably stick more to what we were doing in class last time, which was I give you the standard form and ask you to sketch it.
Thank you, sir.
Okay, no problem. Okay, so let's get into today's material. We're going to talk about first quadratic inequalities. Notice this name, inequalities. So when we were doing problems last class, right? When we were doing problems, when we had to find the x-intercept, let me go back to one of these. When we had to find the x-intercept, step 4, we set the function equal to 0, and that gave us a quadratic equation, right? A quadratic equation, and we either factored it or we used the quadratic formula to solve it, right? But that's a quadratic equation. What we want to talk about today are quadratic inequalities, and these come up in different places, especially in calculus, of course. And you need to know the difference between solving a quadratic equation and solving a quadratic inequality, because it's not the same method. And so students will go to solve a quadratic inequality, they'll do it like an equation, and then it's all wrong. So I just want to remind you, first of all, what inequalities are. And I'm starting here with the idea of linear equations first. So we all know what a linear equation is, right? We have an equation with one variable in it. It's not squared or anything, and we can just move things around and solve for x. Now, if we replace this equal sign with this symbol, this is the less than symbol. This is the greater than symbol. This is the less than or equal symbol. And this is the greater than or equal symbol. So the idea is this. We know that if we want this linear equation, this left side to be equal to 0, we'll plug in 2. You plug in 2, you get 0 equals 0. But if we want to know what x's you plug into this to make it smaller than 0, then it's a little different. What we do with the linear equation to solve, well, with linear equations, all we have to do is just solve it like a linear equation. We just move things around. So we just add 8, get 4x less than 8, divide both sides by 4, and then you get x is less than 2. So that just means that if you pick any number to the left of 2, any number over here in this interval, now remember how we do intervals, -infinity to 2. I do not want to include 2 because this is a less than symbol, not less than or equal. If it had this bar down here, then I would want to include 2. So I would put a bracket here, but because it's less than only, or strictly less than, we will not include 2. So if you pick any number, like if you picked -5, I forgot to put, yeah, that's right. If I pick -5, if I put -5 in here, it will work. I will get a number smaller than 0. That's linear equations. That's linear equations. With linear equations, it's pretty much what you would do with, linear inequalities. That's pretty much, you do the same thing that you do with linear equations. There is one exception though. Do y'all know what it is? Does anyone know this very special scenario where you have to do something? Like, let's say you had -4x less than 8. Let's say you were trying to solve that linear inequality. Does anyone know if you divide both sides here by -4, do y'all know what happens?
You have to flip the symbol.
You have to flip this symbol. If you ever multiply or divide both sides by a negative number, you have to flip the inequality over. And now it becomes greater than, this side becomes x, and this side becomes -2. And students always wonder, like, why do you have to flip the symbol? It has to do with the fact that a negative times a negative is positive, and a negative times a positive is negative. Because of that, when we divide by a negative, we have to account for how the signs are impacted, and it flips the inequality over. So just be careful with that. If you multiply or divide an inequality by a negative number, you must flip the inequality. Okay. All right, so that's linear inequalities. They're pretty much exactly what you would do with the linear equation, with the one exception that if you multiply or divide by a negative, you'll have to flip the inequality. Okay, ready to do the quadratics? Quadratics are different, all right? So let's start out first by recognizing the difference between the quadratic equation, right? This is a quadratic equation, and this is a quadratic inequality. This first one says, okay, for what values of x is this equal to 0? And the way we would do this is by either factoring, or you could also do the quadratic formula. But once you factor, you set each of them equal to 0, and you get your two solutions, 5 and -1. Everyone comfortable with that? Like you could do that, either factor or quadratic formula? Good. Okay, so if we plug in 5, we get 0. If we plug in -1, we get 0 equals 0. So we've got two solutions for the equation. The way you do a quadratic inequality is completely different. All right, not completely, but there's a step, there's a little bit of a procedural thing we have to do at the end. So the first step that we do for any quadratic inequality is we solve the equation first. Solve it as an equation first, which means you're going to write the inequality down, and you're going to replace the inequality with an equation of 0, like equals sign. That's the first thing. And we already know the solutions to this, right? Because I just did this on the side. We have our two answers, right? I'm going to put ... I'll put an arrow. We already know how to do that, right? That part's the same. The second part is the part that's requires a little bit more thinking. What you're going to do now is you're going to put both of those answers on a number line, and you're going to make sure they're in order. So -1 goes first, then 5 over here. And what that does is it breaks your number line up into 3 regions. You have a first region, second region, third region. So the answer that we're going to get is going to be either one of these regions, 2 of these regions, or all 3 of them. It just depends on the inequality itself. So what we'll do now for this second step, after we break the number line up into regions, is we're going to do test points. Test points. So what we'll do is we'll pick any number we want in each of the regions. Okay, so we get to pick any number to the left of -1, so I'll pick -2. Any number between -1 and 5, so I'll pick 0. And any number to the right of 5, so I'll pick 6. And what you have to do with those numbers is plug those into the inequality that you started with and see whether or not it's true or not. So let's test right now -2, okay? And when I test it, I'm testing it into this. So I'm going to put -2 squared minus 4 times -2 minus 5 less than or equal to 0. And this is what I'm actually asking myself. Is this true, right? When I do this computation, will this be less than or equal to 0? So when we square the -2, we get 4. -4 times -2 is +8. And then take away 5. The question, is that less than 0? Well, let's see, 12 take away 5, that's 7. 7 is not less than 0, is it? That's not true. This is not true. And what that means is that we picked this -2 in that far left region. The fact that it came out to be false here, right, tells us that no number we ever pick to the left of -1 is going to work. If you try -3 or -5 or -10 or -100, none of them are going to work. All right. And we have to do that now for each of the regions. So now I'll test 0. Are there any questions? Plug 0 in, no questions? 0 squared minus 4 times 0 minus 5. Is that less than or equal to 0? Question, is it, right? So this is 0, 4 minus 4 times 0, that's 0. So everything goes away except -5. And -5 is less than 0. This is true. Which means that everything that we would have picked between -1 and 5, everything will work. And then we have one more point to test. We test 6. And that'll give us, let's see, 6 squared minus 4 times 6 minus 5 equals 0. Oh, sorry, less than or equal to 0. That's the question. This is 36 minus 24 less than 5. This is not less than 0 because that gives you like 12. That gives you 7 again. Is that right? Yeah, 7, I believe. 12, yeah. Less. This is not less than 0. This is false, which tells us that nothing over here works. Understand? We're not done. We don't have our final answer yet. Do you understand this procedure? Do y'all see how this is much different than an equation? An equation you just solve, it's either factoring or quadratic formula to get you 2 answers. Inequalities, you've got to get your answers, and then you've got to do this number line and these test points and figure out which region works and which doesn't. There's a lot more to this. So now what I'm going to do is figure out, I know it's everything between -1 and 5. So I know for sure anything in here works. What about -1 and -5 themselves? Well, we know that when we plug in -1, we get 0, right? We get 0 when we plug in -1. Well, remember what the inequality was. The inequality had the little bar on the bottom, right? The little bar means it's okay, it's all right. We want it to be less than or equal to 0. So that means we do want to include -1, everything in between. And again, 5 makes it 0, so we do want to include 5 as well. So our final solution written as an interval would be bracket -1 to 5, close bracket. That is the interval of solutions. All right, that's the interval of solutions we have. Give me just a second. Okay. All right, questions? I'm going to show you, I hate to show people the wrong way of doing things, but I'm just going to show you that if you do it the kind of like easy way that you think it is, you'll get the wrong answer. So watch, if you had done this, if you had just left this here, factored this out, and then said, oh, I'm going to take x minus 5 and make that less than or equal to 0, and then I'm going to take x plus 1 and make that less than or equal to 0. That's what a lot of students do. Students that don't know how to solve quadratic inequalities, this is what they'll do, which pretty much follows the same format as this, right? Just instead of using the equal, we're using the less than or equal. The problem here is that if you add 5 to both sides here, you get x is less than or equal to 5. And then over here, if you subtract 1, you get x is less than or equal to -1. So let's take a look at that on a number line. This answer, x less than 5, means if we go to 5, we want to be less than or equal to it, which would mean everything this way, right? Everything that way, forever. And we would include the 5. The other one says if we take anything less than or equal to -1, which would mean anything over here like that, right? Including this -1. So do y'all see that the correct solution is everything between -1 and 5, But this implies that you could actually plug in something like -2, right? Like this is saying, yeah, -2 would work. -2 is less than or equal to 5. -2 is less than or equal to -1. But we already know that when you plug in -2, it doesn't work, right? We already did that. So there's something wrong with this. Well, what's wrong is this is not the way you do quadratic inequalities, all right? And again, it goes back to the whole idea that when you're multiplying two things together, if you had two negatives, you would get a positive. Or if you had a negative and a positive, you would get a negative. And that the only way to actually keep track of that is to do the number line and test the regions. Unfortunately, that's the most efficient way. Questions? Isabella, do you have a question? You look like you have a question.
Can you go back to me real quick?
Say again?
Can you go back to that? Yeah, I'm just gonna take a picture of it.
Yeah.
Just 'cause-
And remember, everyone, I do post these notes online, right? So everything I write here, I will upload. There's a shared folder that you can get to these notes and download. I think I sent an email with the link like a few weeks ago. Okay, so let's try another one. All right, so here we have another quadratic inequality, right? You can see the inequality symbol here. We call this a strict inequality because it doesn't include the equal. That means we have to be bigger than 0. We can't be equal to 0. So, okay, first thing I'm going to do is I'm going to set it up like an equation first. And then I'm either going to factor it or I'm going to use a quadratic formula. Now, I'm not going to take the time to do that. Well, I'm going to factor it because it does factor. So if you needed to do the quadratic formula, that's fine, but I'm not going to. I believe this will factor to be this. Let's see, 2x squared minus 4x minus, yeah, okay, so that's the factoring. And if we set each of those factors equal to 0, we get x equals 1/2 and x equals 2. So those are the numbers, right? These are the numbers. 1/2 and 2 are the numbers that make this quadratic expression equal 0. I don't want that though, right? I want bigger than 0. So now the second step is to draw a number line, plot my points in correct order, so 1/2 comes to the left of 2. That will partition my number line into 3 regions. And now I have to pick 3 test points. So pick good test points, like something to the left of a half, a good number there would be 0, right? A number between 1/2 and 2 would be 1. That's a good number. And then something to the right of 2, pick 3. You could pick any number you want. It does not have to be these. They just have to actually live over there on the left or right or in between. And now you test them. So let's test 0 first. Well, if we plug in 0, all the 0 stuff goes away, so you just get 2 bigger than 0, and that's true, right? 2 is bigger than 0. So that means this region is good. And then I plug in 1. I plug in 1, I get 2, I get 2 times 1 squared minus 5 times 1 plus 2. Is it bigger than 0? Let's see. 2 minus 5 plus 2 bigger than 0. Uh-oh. -1 bigger than 0. No, this is false. Right? This is not true. Which means the middle region doesn't work. And in an effort to save time, I'm not going to test 3. I'm just going to tell you what the result is. It does work. All right. Not showing that. So do we want to include 1/2 and 2? Do we want 1/2 as part of our answer and 2 or not? Do I want the number 1/2 plugged in?
No, sir.
Careful, careful. If we plug in a half, doesn't that give us 0, right? If we plug in a half or we plug in 2, we get 0, right? And the inequality says we have to be bigger than 0, right? Bigger than 0. So we do not want to include a half. We do not want to include 2, but we want everything here to the right of 2 and everything here to the left of a half. So writing that as an interval, it would look like this: -infinity to a half unioned with 2 to infinity. So give me any number to the left of a half, it'll work. Give me any number to the left of, sorry, to the right of 2, it'll work. Questions? Okay, we're good, we're good.
I do have a question.
Yes.
Why is it why is it closed in a parentheses and not a bracket?
Okay, so remember, see here in yellow where it says that we want this whole thing here to be bigger than 0, right? Bigger than 0. Well, the first thing we did is we asked ourselves, when is it equal to 0, right? We said, okay, well, let's figure out, we want to know when it's bigger than 0. Let's first figure out when it is 0. And we said, okay, at 2, it's 0, and at half is 0. But we don't want it to be 0. We want it to be bigger. So that means we cannot plug in 2 and we cannot plug in 0. That's why I left these little holes open, right? And anytime we don't want to include the point, we put a parenthesis. If we did want to include the point, we would put a bracket, like the previous problem. We did want to include -1. We did want to include 5. So that's why I put brackets on the 2 numbers.
Okay.
Is that clear?
Yeah.
Okay, good. Any other questions? I've had 2 questions today. Good job. At least 2. Okay, let's see what we got next. Yeah, okay, so that's it for quadratic inequalities. There's really nothing more. The steps are the steps. You just have this additional thing where you have to do a number line and you have to take your test points, check your regions, and then put your answer as an interval. All right. Now, do you want me to proceed or would you like me to give you all one to work yourselves? You want to practice one or what? Yes, I'm seeing yes. Okay, so how about I give you this one? I want to know, I'm going to make this a little tricky. Not terrible, but just a little bit. Let me see. So let's go 2x squared less than hold on, I got to make sure this works. 7x minus 3. So I want you to solve this. It is a quadratic inequality, all right? The trick here is the first step is you got to move everything to one side and get a 0 on the other side. So my recommendation here would be to move the 7x and the minus 3 to the left and make it a 0 and then start the procedure. Does that make sense? Subtract 7, add 3 to both sides. Subtract 7x, add 3, and then work it out. I'll give you a few minutes. Why don't you on the poll let me know if you finished, when you finish the problem, just click yes, okay? And that way I get some idea of how long this is taking. So I just put all the work up here. If you're working it out right now, you can just kind of look at it and see how you're doing with it. We'll just go another 30 seconds.
So if you plug 3 into the equation, wouldn't the 3 be greater than 0?
But if I plug 3 into what?
If you plugged in 0 into the equation, wouldn't the 3 be greater than 0?
Oh, you know what? I read the inequality wrong. I'm so sorry. I apologize. My interval's wrong. Oops. Thank you for pointing that out. Javier just pointed out this inequality was less than 0. I don't know why it was. I think because the last problem was greater. Is that what it was? I was trying to move too fast. Let me see. Yeah, last one was greater. Sorry, I was going too fast. Okay, we wanted less than, so that's opposite of this. So we want, it's going to be no, yes, no, which changes this. Okay, so it's everything between 1/2 and 3, not including the endpoints. That's why I was looking at your face, some of your faces, y'all were like, what? What the hell? Okay. We good? Questions on any of these? What I did was, on the first one, I factored it. I didn't show any steps for factoring. I just did it. But if the factoring is causing you trouble, you could use a quadratic formula. Crank out the 2 solutions, 3.5. The good news, quadratic formula always works. Bad news, it takes about twice as long to do. So, you know, when it comes to a test, that eats up some of your time. Anything else that you want me to address here? We're ready to move on. Okay, let's talk about the next major topic, which is polynomial functions. And I mentioned this at the beginning of class last time, that the big picture was that we wanted to be able to sketch lines, quadratic functions, which we now know how to do, right? We know how to sketch lines and quadratic functions. The next topic was polynomial functions. And then I'd highlighted rational functions because those are the hardest or most time consuming. There's quite a bit with a polynomial function though. These are going to be, up to this point, this is going to be the hardest thing to do. All right, polynomial functions in general. So first of all, what is a polynomial function? So we've studied 2 types of functions so far. We've done linear, right? And we've done quadratic. And we should be comfortable graphing both of those. Well, I'm here to tell you that both of those are actually polynomial functions because they fall into a broader category of functions called polynomial functions. So polynomials, the word polynomial, poly means many, and nomial means basically terms. So you have many terms. So if you look at a linear expression, you have 1, you have 2 terms. With the quadratic here, we have 1, we have 2, we have 3 terms. Well, a polynomial is an expression that has a bunch of terms where you have x raised to all sorts of different powers. So let me give you examples of polynomials. Those are 2 examples. Like this is the first example of a polynomial function. Notice the highest power in x we see here is 1. Here's another example of a polynomial function where the highest power we see is 2. That's called quadratic. And then we could just keep going. Like I could do a polynomial that looks like this. how about something like 3x, let's say negative 3x cubed plus x squared minus 1. That would be a polynomial function. I could do another example. Oh, notice here the highest power we have is 3. Another example, I could do something like h of x equals 4x to the 10th minus 8x squared plus x minus 4. That's another example of a polynomial function. So what all polynomial functions have, okay, what they all have in common are a bunch of terms where you have x raised to these powers. And if you have x raised to these powers, you're going to have a highest power, right? And I've circled in all of these, I'll highlight them. The highest power of x in all of these is actually something important to us. It's gonna help us. So in general, I'm gonna write what a general polynomial looks like, okay? I'm gonna write a general polynomial now. When I write it, most students, they throw up because it just looks so strange. So here's what a polynomial function looks like in general. Well, it's some function f of x. And then we are going to have some number, right? Notice all of these have some number in front of that x term, whether it be a 3 here, here it would be a 1, here it would be a -3, here it would be a 4. So it's just going to be some number in front of x to a power, right? Some number in front of x to some power. I don't even know what the highest power is. So here's the way I'm going to write this. A x to some power n. That power could be 1, it could be 2, it could be 3, it could be 10, it could be 30, it could be 100, it could be 10,652. The highest, there is no highest power that you could ever have on a polynomial. It can be as high as you ever want it to be. All right. So in general, it's some number in front and then x to the n. Plus, now you're going to have another number in front of x, but now the power is going to be less than 1 less than what this was. So like we went x squared, the next term had an x to the first power. Here we had x cubed, the next one went to x squared. Wait a minute, how about on this one? We went from 10th power, do y'all see a 9th power here? You don't, do you? But it actually is. Right next to this, it's not written, is 0x to the 9th. Right? 0x to the 9th is sitting there. Now, we don't write it, but it's important to understand that we do have a number in front of x to the 9th power. That's what this is saying. We have a number in front of x to the 9th, right? This would be 4x to the 10th plus no x's to the 9th. And then this pattern just keeps going, plus c, now the next power down, n minus 2, which would, on this example, would be the 8th power, wouldn't it? And we don't have an 8th power, so it would be a 0 in front of it. But I can keep on going, right? And then I have a d x to the n minus 3, and the power just keeps coming down and down and down. So I'm going to put plus dot dot dot, meaning that this keeps happening until I get down to, I don't know, some number in front of x. I'm going to leave a blank in front of here, and then plus just some number. So notice on all of these, well, some of them have x, you know, like -4x and then a number by itself. This one doesn't have an x term, but it has a -1. This one has an x and then it has a -4. So that's like the very tail end will be an x. It may or may not be there, but the power has come down all the way till you get down to a final like number, if there is one. Make sense or not? You don't need to be too invested in what's going on here. Just get the general idea. Now, there's a problem with what I just presented to you. There's a problem. This is not actually the way we write polynomials. I'm just trying to get you to understand the idea first. The problem is this: what if the power on this is 100, right? Then we would have ax to the 100 plus bx to the 99 plus cx to the 98 plus dx to the 97, what's going to happen? If I keep doing that all the way down to the powers go away, what's going to happen? Ax to the 100, bx to the 99, cx to the 98. What's going to happen? Think about it. I always ask my class because I want to see if anyone can figure out what's wrong with writing it this way. Let me give you a hint. If I use a power of 20, I don't have a problem. 21, I don't have a problem. 22, I don't have a problem. It's right when I get around 24, I'm going to have a problem. How many letters are there in the alphabet? 26, right? Okay, so I'm already using an X and I'm already using an N, right? So I can't use those, which leaves me 24 letters. So if I say A, then B, then C, see if it was 100 power, right? I have A, X to the 100th, then B, X to the 99, and C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? And I mean, well, no N, I can't use the N. So L, M, O, P, Q, R, S, T, U, V, W, I can't use X, so Y, Z, and then I'm out of letters, right? So this doesn't make sense to use B, A, B, C, D. So here's what we do instead. We don't do this, okay? We don't do this. We do this. We write, okay, a polynomial function is going to have X to the N, and in front of it is some number, right? We were calling it A, but now I can't use the letters, right? I can't use letters like that because I'll run out. So instead what we do is we write A subscript N. That's the nth coefficient. It's the coefficient in front of X to the N. Then I write B, A sub N minus 1, X to the N minus 1. Then A subscript N minus 2, X to the N minus 2. And I keep doing that until I get down to A sub 1, X plus A sub 0. So instead of using A, B, C, D, E, I'm using A subscripted with the same power. So I just want to give you an example. If, let's say, N was 10, then a general polynomial function would look like this. It'd be some number I'm going to call A sub 10 in front of X to the 10th, plus A sub 9 in front of X to the 9th, plus A sub 8, X to the 8th, plus dot, 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 I get down to A sub 1, X plus A sub 0. And see, the thing about subscripting is you'll never run out. You could have A, subscripted with any number you want, 10,000 if you want. And so you will not exhaust your alphabet that way. It's weird, right? I mean, this is a pretty nasty looking thing, but in math, we do things for reasons. We're not just trying to make it look nasty and ugly. We're doing it because we have a finite alphabet. So subscripting is the only way we can go. Okay, I need to clarify some things. On a polynomial function, we have some restrictions, all right? The first restriction is this. These n's, all of these powers, right? All powers must be non-negative integers. In other words, the powers have to be either 0, 1, 2, 3, 4, okay? The powers have to be non-negative integers. If you have a negative number as an exponent, as a power, it's no longer a polynomial function. To be a polynomial, all the powers have to be non-negative integers. The other condition we have, and this one I think is a little more obvious, is that the number in front of the highest power right there, this number right here, A sub n, cannot be 0. Because if it's 0, then you don't have this, and then you don't have a highest power. This is not your highest power. That is, this a sub n is called the leading coefficient. And n, the power, whatever power we have right there, that is called the degree of the polynomial. It's the highest power. The highest power that we see. So if we go back up here and we look at the 4 examples I just gave us, the blue numbers here, the blue numbers 3, 1, -3, and 4, those are the leading coefficients of those polynomials. The 1 is the degree of this linear function. It's a degree 1 polynomial. A quadratic is a degree 2 polynomial. This would be a degree 3 polynomial, and this would be a degree 10 polynomial. All right. Notice in all of these polynomials, if you look at all the powers, x squared, here's x to the first, x cubed, x squared, x to the 10th, x squared, x to the first. Notice all the powers are positive integers. There's no negatives, no fractions. So these are all polynomials. Okay. You think you have a general idea of what a polynomial function looks like in terms of written down? Now, the question is, what do they look like when you graph them? And the answer is, well, it depends on the polynomial. They can look very different from one another. We already know what a line looks like, right? I mean, that's a straight like that. We know what a quadratic looks like. It's a parabola up or down. So what about these higher degree polynomials? What do they look like? So let's investigate that. All polynomials are smooth and continuous. So what I mean by that is that they can be drawn without picking up your pencil, okay? They're smooth in the sense that they don't have like jagged edges on them. There's no sharp corners. Everything is smooth. And you can't pick up your pen. You don't have to pick up your pencil when you draw that. So if you draw a line, right, I think we'd all agree that that's smooth. There's no like ripples or jagged edges. And you can draw it without picking up your pencil. Same with the parabola, okay? Same with the parabola. It's smooth, it's continuous. You can draw it without picking up your pencil. Now, if the degree, remember this n stands for degree. If the degree of the polynomial is bigger than or equal to 2, then I guarantee that the graph will be curved looking. So it'll be curvy, which means these things will start to look like this, or maybe like this, or maybe like that. Kind of like the stock market kind of thing, you know, it's just kind of like these, but smooth, right? Just kind of like up and down and, you know, these ripple effects. That's what polynomials look like. The higher the degree, the more ripples you have, generally speaking. So our goal is to be able to graph them. And graphing these is not super easy, all right? It's actually pretty complicated. It's kind of difficult, all right? So to graph them, the first thing that we're going to use to help us graph them is what's called the leading coefficient test. Now, this is something that you're going to want to copy down and have on your reference sheet, like when the next test comes, right? You're going to want this so that you can use it when you get to the graphing of the polynomials. So let me explain what this leading coefficient test is. I call it LCT for leading coefficient test, so I don't have to write that out over and over. So here's the way the leading coefficient test works. This test tells you, okay, let me explain this. This test tells you about what we call the end behavior. The end behavior of the polynomial. All polynomials are going to do one of four things on the edges, okay? On the edges of the polynomial, the ends, when you draw them. Either both sides are going to go up, or both sides are going to go down, or the left side's going to go down, the right side's going to go up, or the left side's going to go up, or the right side side's going to go down. Those are the only four possible things that can happen with polynomial functions. All of them. Both sides up, both sides down, left side down, right side up, left side up, right side down. That's it. There's no other things that can happen. Now, in between, like in the middle of the function, I put question marks because there can be all sorts of weird undulations and ripples and curves. This is the leading coefficient test only tells you about the ends. Like, oh, my left side eventually is going to go up forever or down forever, or the right side is going to go up forever or down forever. And the way this works is that all you have to do is inspect two things. You look at the leading coefficient. If it is positive, then you're going to have one of these two cases. Now, to determine which of these two it is, you then inspect the degree. If the degree is even, then you'll have this happen. If the degree is odd, you'll have this happen. And then if the leading coefficient is negative, then again, you'll have one of two things happen. And then you go look at the degree to tell which of the two it is. So you're inspecting two things, the leading coefficient and the degree, and then you're figuring out where in this table you are. Make sense? And we're going to do an example, but just want to make sure you'll have the table. I'm going to copy the table down so I have it, and then I can use it over here. Just remember, it only tells you about what's happening at the edges. It tells you nothing about the middle. All right. Looks like I didn't have to copy that. So here we go. Here are the steps. So remember how last class I gave you steps to sketching a quadratic function, right? We went through and we got these steps. I would write that down on my reference sheet, right? I would have those steps. But now for polynomial functions, we have a new set of steps. You cannot use the same set of steps. This is only for quadratics. This is how we do polynomials. So the first thing we do for a polynomial function is we use the leading coefficient test to determine the end behavior. And remember when we were doing quadratics, our first step was to determine up or down. This is kind of like the same thing. We're just trying to figure out like what happens on the edges. Is it up, down, left, right? Like what is happening, right? That's what we're going to do first. And then, let me erase that. After we figure that out, we're going to try and find any x-intercepts. Well, to find x-intercepts, we have to set the function equal to 0. And that is going to be the challenge. That is going to be the hard part for us because this is now a polynomial. It's not a quadratic. So we can't use our standard factoring and we can't use the quadratic formula because it's not necessarily going to be quadratic. So this, don't worry about what I have written down right here, right now. I mean, well, don't worry about this part, okay? For now, just stay tuned, okay? I will explain what we're going to do here. We're going to try and find these x-intercepts. After we find them, which I'll explain as we work through this, then what we have to do is to determine what we call the multiplicity of each of the x-intercepts. And so the multiplicity is really going to determine at our x-intercepts whether or not our graph will cross through the x-axis or bounce off the x-axis. Again, don't worry about that. I'm going to go through it with an example. And then the final step will be to draw our picture. So that's the procedure. Let's do an example so you can start to feel this out, okay? I want us to sketch this. All right, So the first thing we have to recognize, this is a polynomial function, right? This is not a quadratic. So the first thing I'm going to do now is I'm going to use the leading coefficient test to determine the left and right hand behavior of this. So what is the degree of this polynomial? Araceli, are you there?
Yes.
Okay, what's the degree of this polynomial?
Would it be 4?
4, that's right, the highest power of x. Okay, what about the leading coefficient? Which really, Araceli, all that means is what's the number in front of that x to the 4th power?
1.
1, okay, so that's 1. Okay, that's it, good. So we determine the degree and the leading coefficient. Now we go to the table. Here's the table, right? Araceli said that our degree was 4, right? Which means it's an even, right? The degree is an even number. So it's either going to be this or this. And then the leading coefficient was 1. So the leading coefficient was positive, which means it has to be this one. Make sense? So we have this degree is even and the leading coefficient is positive. And so I know that the left side goes up. In the middle, I'm not sure what happens, but the right side also goes up. That's what I know so far. The next step is to find the x-intercepts. And to do that, we set the function to 0. And this is the part that's going to be a little bit of a pain, because now we're really going to test your factoring abilities. So when it comes to factoring, which is something we don't spend a lot of time on in this class. I mean, we assume coming into 1414 STEM college algebra that everybody here has some background in factoring. But realistically, I realize a lot of you are weak with factoring. My calculus students are weak with factoring. So I'm going to walk you through this, but this is where you would want to take that opportunity to go get tutoring or help if the factoring is an issue. All right. The first step for factoring anything is greatest common factor. You look to see if all the terms have something in common. And let's see, Michael, you there, Michael? Michael G?
Yes, I am. Sorry.
Okay, no, it's no problem. Michael, greatest common factor is something that all of these terms have in common. Look at
For
all
the
these-
second one,
Say again?
you said for the second one?
For this equation here on the left-hand side, these 3 terms, can you pull out a greatest common factor? Something they all have in common.
X.
Okay, they all have 1 x. Do they all have 2 x's?
Yes, 2 X's.
Do they all have 3?
No.
No. So you pull out the greatest that you can pull out, which would be 2 x's. Okay, good. So I'm going to pull out x squared, right, like that. And then what will be left is x squared minus 5x minus 14, because we have removed 2 factors of x from each of the terms. Now, once I do that, do you all notice that what's in parentheses is quadratic? And we might be able to factor that. We can actually. X minus 7, x plus 2 is what that factors to be. So look, you have to really make a note here to yourself. If you're having trouble with going from here to here, you really need to invest some time practicing that, okay? And that, if you want, go to the tutoring lab, come to my office hours. If you're going to tutor, say you need practice factoring trinomials, okay? Quadratic trinomials, and you know, the AC method or whatever they want to teach you, whatever. You need help with it. because that'll really slow you down on a test if you can't do that. Now, once I'm here factored, now that there's really nothing else I can factor, it's completely broken down. I have three things being multiplied together that all equal 0. So just as we did before, I'm going to set each of these factors equal to 0. Let's solve. This has a solution x equals 0. The only number you can square and get 0 is 0 itself. This has a solution of 7, just adding 7 to both sides. This has a solution of -2. Okay. Questions there? All right, now this is not part of the steps, okay? This is not part of the steps. I just want you to think about where we are right now. Okay, I want you to just consider where we are. Let me take these answers. Don't write this down. You can do this on a separate page if you want, but I want you to think about what we have. We have these x-intercepts, right? And we know the left side goes up and the right side goes up, and in the middle, we don't know what happens, right? That's where we are. So if we were to try and graph this right now, here's what we'd have. We know that at 0, we have an x-intercept. We know that at 7, we have an x-intercept. And we know that at -2, we have an x-intercept. Agreed? We also know that the left side has to go up and the right side over here has to go up. So this right here is not enough information to finish drawing the graph. It's not. It could do this, right? The graph could do this. It could go down, maybe go up. Let me see it. Uh-oh. Do y'all see that I can't go down and back up? Why can't I do that? Isn't that an x-intercept right there that I just created? I only have 3 though. That's not, I can't do that. Which means I'd have to do something like this. Maybe go like down and then up, and then maybe instead of crossing through, just kind of like bounce off the x-axis and go up. That could be it, right? That could be it. Or it could be this. You could have done this instead. Come down and you could have bounced off the first one and then cross through this one and then cross through that one. You could have done that. That still works, right? There's other ways I could have done cross through here, come up, bounce off, and then go back up and go like that. I could do that as well. There's all these different variations of what could happen. And what's dictating that is whether or not at each of those 3 x-intercepts, I'm either crossing through or bouncing off of it. That's what's dictating it. Those different variations in the drawings are all about what happens at that x-intercept. And the idea of either bouncing off the x-intercept or crossing through the x-intercept comes from this idea of called multiplicity. And so let's address that, because that's the 3rd step in the process of graphing these things, is to determine multiplicity. So we've found the x-intercepts, okay? And now we're going to determine multiplicity. So what the hell do we mean by multiplicity? Here's what we do. We go back up to the step that we had it factored in, right? This step right here, where we have it factored completely. That's where we have it completely factored. And what we do is we look at each of the factors and we look at the power on the factor. So if you look at this first factor, x is raised to the 2nd power, right? 2nd power. This x minus 7, that's a factor, is raised to the 1st power. And this x plus 2 is raised to the 1st power. Those numbers, 2, 1, and 1, those are the numbers that are going to dictate whether or not we bounce or cross. If this number is even, if it's an even number, we will bounce at that x-intercept. See, because the x squared is where we got the 0 from, right? The x squared is where we got the 0 from. So the fact that that's a 2 here, that tells me that when I get to 0, I'm going to bounce. If the number here is odd, then that tells me here I'm going to cross through. This number is also odd, which means here I'm going to cross through. Does that make sense? Even power, bounce, odd power, cross. Yes? Even bounce, odd cross. Be careful. The biggest mistake students make on this is instead of looking at the powers to figure out if it's even or odd, they look at the number. They say, oh, X is 0, that's even. So I bounce. And they say, oh, this right here, that's 7 is odd, so I cross. And they say, oh, -2 is an even number, so I should bounce. You're not looking at the numbers. You're looking at the powers of the factors from where they came from. Once we have this multiplicity set, we're ready to draw. Okay, here comes the graph. Now, these graphs are going to be sketches. They're not super precise. They just give us a feel for what's happening. I'm going to put my x-intercepts as I did before, 0, 7, and -2. I know the left side goes up, so I'm going to put a little up arrow over here, and I know the right side goes up like this. And notice when I drew those arrows, I drew them to the right, like this one is drawn to the right of the furthest point to the right. So here was 7, I came to the right a little bit, and I know I have to go up over here. The -2 is my furthest point to the left, so I came to the left, and that's where I put my arrow. Now I'm going to start to draw. I'm going to draw, and I'm going to connect this side to -2. And when I get to -2, according to the multiplicity, I'm going to cross through. So I'm going to go through and cross through just like that. And now I'm going to have to curve back smooth, right? Remember, polynomials are smooth and curved. So I'm going to curve back towards 0. But when I get to 0, what does the multiplicity tell me I'm going to do? Bounce, right? Bounce off. So watch how I draw this. I'm going to go up and I'm going to bounce off and come back down. And then I'm going to continue to connect this smooth and continuous to 7. When I get to 7, according to the multiplicity, I should cross through. So I'm going to cross through there. And once I cross through, you can see I can make a nice smooth connection with this side over here. That is the general graph of that polynomial function. Let me stress to you what we are capable of doing in this class and what we're not capable of doing. What we can do with this picture is you can tell me from just looking at this, you can tell me the domain, you cannot tell me the range, okay? You can tell me the x-intercepts. You can tell me where the graph is above the x-axis. You can tell me where the graph is below the x-axis. What you cannot do is this. You actually don't know how low this goes, okay? And you don't know how low this piece goes. You have no freaking idea how this goes. So everyone's picture is going to look slightly different. We should all go between here, these 2 points, we should all come down and we should all bounce off 0 and come back down. How far you go down though is completely up to you. It's not like with the parabola. You know what the parabola from last class, we know the highest and lowest points. We have the vertex. Well, in college algebra, there's no way to determine the highest and lowest points on a polynomial function. It's not possible. In fact, that's one of the main goals of calculus, is that if we have a polynomial, can you find me all the hilltops and all the valleys of the polynomial? Can you find me the peaks and valleys, highest and lowest points? And we have to spend weeks doing that. In my Cal 1 class, we haven't even gotten to that point. We're about to do it, but we're like, what, in the 5th, 6th week or something? And we still haven't gotten to it yet. We've just been building up to it, building up to it, building up to it. We're almost there. So everyone's graph's going to look a little bit different, all right? But we should all have the same x-intercepts. We should all have the same bouncing and crossing, and we should all have the same end behavior, all right? And don't forget, your graph needs to be a function. Like it needs to pass the vertical line test. So when you're done drawing your picture, make sure you have a function there. All right, let's see here. So here's the good news. The good news is this. The set of steps, there's not that many for a polynomial. You determine the left and right-hand behavior using the leading coefficient test. You find the x-intercepts. You determine the multiplicity, which is bouncing and crossing, and then you draw your picture. There's really not a lot to do here. It's actually, you could argue it's almost less steps than the quadratic, because quadratic we had to do up or down, right? Vertex, so you had to find HK, then you had to find the x-intercepts, then you had to find the y-intercept, and then you had to put it all together. This looks like less steps. It's actually a lot more work, as you're about to see in the second example, because we're going to run into a complete freaking nightmare now. All right, here we go. It looks intimidating, right? I mean, if you're asked, hey, sketch this function, give me a picture of what this function is. And before we get too far into this, sorry, I forgot to close the poll. Before we get too far into this, remember when we were talking about quadratic functions, and I kind of gave you some real life examples of where quadratics are, come into play. I didn't talk about polynomials, but you can just think about anything in the real world that has some sort of up and down behavior. Stock market, price of gas, price of milk. I mean, just anything where you have the up and down sort of trending things. Polynomials are perfect for modeling those sorts of situations, right? Did I tell you all about my goal, my weight loss goal? Did I tell you all about that? Yeah. What did I promise y'all? Did y'all forget the promise?
Wasn't it like if you lose 12 pounds by a certain time, we'll get like extra points on the exam? I just forgot what.
I said 3 weeks ago, tomorrow. So today's day 20. Tomorrow will be day 21. I said 3 weeks ago, my goal is to lose 12 pounds in 12 weeks. If I can do that, then I'll give everyone 5 points on the final exam. I'll give everyone a 5-point bonus, right? So I actually hit 12 pounds today. So I've done it in 3 weeks, which is way ahead of schedule, which is good. The reason I'm bringing this up is because, let me see here. Let's see if I can do this. I don't want to go too much into this, but where is it? Where the hell is it? There we go. I know y'all can't see this yet. Hold on. All right. Trying to figure out how much of this I want to show here. Oh no, that didn't work. Give me a moment. I'm almost done. Hold on. That should be good. Let me see how this looks in here. Okay, so this is basically just a real quick graph of my weight loss. All right, I'm not including my weight right now. I'll show it at the very end. At the end of the semester, I'll show you what I started at and what I finished at. Okay, but this is my data. I take my weight every day. So what I can do is I can ask the computer to add a polynomial function model to that graph, and I can pick what's called the order, which is the degree of the polynomial. Right now it's trying to fit a parabola to that data. If I do a cubic, that's third degree polynomial. You see that it's trying to fit some sort of, it only goes into 6th degree, but do you see this is a smooth curve that kind of gives me a trend of what's happening? Kind of, yes? That's the way we use polynomials in the real world. We get data, and then we fit a polynomial to it, and then we go and investigate that polynomial. Now, I will say, weight loss, polynomials are not good for modeling weight loss, because remember what happens at the edge of a polynomial. It either goes up or down forever, right? And your weight loss is not going to go down, just drop off and you become zero, right? That doesn't ever, or you're not going to go up to infinity. So it's probably better to use like a logarithmic or an exponential model instead, which is what you would normally use. But, you know, I'm just trying to show you that if you have data that goes up and down, you can fit a polynomial to it. So we like to study these things. Let me just back up for a second because I changed a bunch of stuff on this graph. Okay, there we go. I don't want to mess up my stuff there. All right. So look at this thing. Let's just do the steps. First step, leading coefficient test, right? So let's see, Zachary, I'm trying to call on people more, but Zachary, you there?
Yes, I am.
For leading coefficient test, what are the two things you're gonna look at?
We're gonna look at the highest coefficient.
Highest power,
Yeah, highest power.
which is called the degree, and then the leading coefficient. So what is the degree of this polynomial?
That would be 5.
5, okay. And then the leading coefficient?
-1.
-1, yeah, it's the number in front, -1. Good. Now, when we look at our table, right, our little cheat chart here, we're looking at the degree, we're looking even or odd, and leading coefficient positive or negative, right? That's what's happening. So when we look at the one that we have here, the degree here, 5 is an odd number, and the leading coefficient is a negative number. So let's see. How about Caitlin? Are you here, Caitlin?
I'm here.
Okay, Caitlin, did you happen to jot down that chart? Let me just put it up here. If we have an odd degree and a negative leading coefficient, can you tell me what happens to left and right hand sides, Caitlin? We have odd degree and negative leading coefficient.
That would be like the last square on the degree one, on the degree
Okay.
odd.
Okay, so does the left side go up or down?
Up,
Okay, and the right side?
down.
Okay, good. So it's this one right here, right?
Okay.
Left side up, right side down. That's what we know so far. That's all we know, is that the left side goes up, the right side goes down, and in the middle, who knows, right? It's going to do a bunch of, you know, crossing, bouncing, who knows? All right, next step. Oh, and this is the part that's going to be bad. We need the x-intercepts. And so we have to set this big, nasty, ugly thing equal to 0. All right, now, like we had talked about last time, the first thing we always want to do is GCF. So Michael, are you there? Did I call him Michael already? Did I call Miguel or Michael? Or someone else? I called Michael G, didn't I? Maybe I'm losing my mind. I am. Jose? How about Jose?
Yes, sir.
Okay, do you see GCF?
Yes.
Okay,
was
what
about
do you
to-
see? Go ahead.
I was about to start working on it to do it.
So look first, look at all this. Do you see a number they all have in common? But all the numbers this is like a -1, right?
-1, yeah.
So
With that -1 and let's see,
how about x's, Jose?
x's
How many x's do they all have in common?
4.
They all have 4 X's?
No, no.
What's the most number of
2,
X's?
I'm sorry, 2.
2. Yeah, they all
Yeah.
have 2 X's, right? So we can pull out an X squared.
Yeah.
We can do that. Now, the question is, if we do this, right, what will be the first term here when we pull out an X squared from here? Because it was a negative X to the 5th, what would we have here?
Positive 1 x to the 5th. No.
Well, we took 2 of the X's away, right?
Yeah.
So we should have an X to the 3rd
X
now,
to the 3rd.
but it should still be negative, right?
Yeah.
Because when you multiply this through, that would give you the negative X to the 5th.
Mm-hmm.
Now, my recommendation is that when you do this GCF, if your first term is negative, then don't do that, all right? In other words, do this instead. Pull out a negative X squared,
Okay.
okay? And that's what that's gonna do is it's gonna keep, now it's gonna make this first term positive, which will help with factoring in a minute. So I pull a negative X squared out of each of these. That has the effect of changing all the signs. So this used to be negative, now it's positive. This positive 2 now becomes negative 2.
Negative.
And how many X's did I pull? I pulled 2 of them, right? So I'm left
Yes.
with X squared, right?
Yeah, x squared.
And then let's see, let's let someone else. How about Isabella? Are you there?
I actually have a question.
Yes.
So why wouldn't we technically get the negative from the same 36? You know what I mean? Since we already got the 2 from there.
Well, we haven't gotten down to this one yet. So what we're doing is we're noticing that every one of these terms has a negative X squared in them.
Mm,
And we're pulling it out of each one of them. And so when I pull a negative away from this, I'm left with a positive. And when I pull 2 of the X's away, I've got X cubed. When I pull the negative away from this, I still have the 2, but it's now negative. And then I pull 2 of these X's, so I have X squared.
Yeah.
Same thing here. I pull the negative away. I'm going to now have negative 15 and now just an X because I pulled 2 of the X's away.
But yeah, no. So what I'm asking is, you know how when we find, because so I don't know how to word this. I'm sorry.
It's okay. I'm trying to.
I understand it, but so since we got the 2 and put it in the front, that's what
The
I'm
X2.
saying. Yeah, the X2 and put it in the front. That's what I'm saying. Why wouldn't we say it's coming from that 36 instead of the negative 1x? The way I'm wording it is confusing. I'm sorry. I understand it.
Okay, so if you understand, what's this last term?
36x or positive 36x.
Positive. I agree with positive 36, but why are you saying X?
Oh, no x. Would
Okay,
it just be
good. All right.
36?
Yes, that's right.
Okay.
Okay, good. If you can think about your question, maybe reformulate, maybe I can help you out. I'm having
I
trouble.
will.
Okay,
I'm
all right, just let me
sorry.
know. It's okay. So here's where we are, and we only have 4 minutes, okay? We only have 4 minutes. So when we look at this, what we have to do now is see if there's any way we can factor this. And we have to recognize that we have 4 terms. And does anyone know that what we do when we see 4 terms? If it's 3 terms, we do, you know, like AC factoring, trinomial. Dominic's going like this. Grouping. Now, I have to stress this. Grouping does not always work. When we see 4 terms, we try grouping, but it won't always work. And in this particular problem, it won't. And so we are going to face something that a lot of you who've learned factoring in the past when you couldn't do, when grouping ever failed, you normally just stopped and said you can't factor it. But we actually will be able to factor it, but we have to teach a brand new technique for factoring. So this is what we're going to talk about next time because we don't have enough time today. I just want you to know right now, we're kind of stuck, all right? So next class is going to be all about this thing called synthetic division and how we use it to factor, all right, next time. So because we weren't able to really get that far, here's what I'd like for you to do for homework. On the online system, go ahead and do the homework for quadratic inequalities. So 4.5, go ahead and do that homework online. Other than that, don't do anything else online for homework. Instead, I want you to try and just do a couple of problems here. So for homework, I'm going to give you 2 problems. I want you to sketch both of these. These are polynomials, and both of these polynomials you can factor by hand. In other words, you don't need any special synthetic division or any sort of grouping or anything like that. This will just be factoring, I think, that is within what one should expect from a 13 or 14 STEM student. So first one, how about f of x equals, let's go negative x to the 4th plus 25x squared. That's a weird one. Just follow the steps, okay? The steps are leading coefficient test, right? Determine left to right behavior, find the x-intercepts, determine the multiplicity, bounce across, draw it. See how it goes. And the other one will be f of x equals, let's say, I'll keep it positive. How about 4x to the 5th minus 17x to the 4th, yeah, plus 4x to the 3rd. Okay, you're free to go. I'll post these notes right after class. In fact, I'll post them right now.
Thank you, Professor. Have a good day.
Have a good day, everyone.
I have a question.
Yes.
For 4.5, when will that be due? Tomorrow or tonight?
Tomorrow night. I
Okay.
think I'll have to check the deadlines. Well, it'll be due whenever it says it's due, but I'm pretty sure I pushed it till tomorrow night.
Okay.
Yeah.
Sounds good.
Okay.
So
Alrighty.
for the
Thank you, sir.
For the tutoring hours, I know you sent us the link. I copied it down. But what
It's
are
in the syllabus.
Okay.
Yeah, if you look at the syllabus, there should be a link. You can also just go to the math lab, the NVC website and just type in math tutoring up in the search bar, and it'll bring you up links.
Okay.
And it'll be, they have on-campus tutoring and Zoom tutoring.
Okay. And
I would just tell them, help with factoring, and they'll kind of lead the way. They'll help
I
you.
think I figured out how it's just best to show you my question.
Okay.
So, you know how this is the, what is it called? The greatest common factor, right? Or
The x squared is, yes.
yes. So this is the one that they all have in common, right?
Yes.
So we took just this and put it there.
Yes.
But since this was the negative already, we got the negative from here. Oh, sorry. We got the negative.
Yeah, no, I understand. Now I
the
understand.
negative from there. So
I got you.
even
Okay,
so we're saying if this 36 was positive and this was still negative, that it would still be the negative, right?
Yes.
Okay, okay.
Look,
That's
let
just-
me show you something real quick,
Okay.
if you have a minute.
I do.
I want to, let's do it backwards. Let's say I had this. Okay, what if I asked you to multiply this out? In other words, multiply the -5 through like this. Okay. When you multiply the first one, well, you know what? Let's put an x next to that 5. How about that? -5x. If I ask you to multiply the first one through, you get -5x cubed. Do you agree?
Yes.
Okay, and then the next one, we would get what? And the second multiplication through.
Would it be this? Would it be the same thing?
It would be -5, right?
Oh, wait, -5 squared?
X squared, yep, okay. And then what about the last one? So do the numbers first. -5 times -4, that would give you what?
20.
20, okay.
And then